At the outermost reaches of our cosmic neighborhood lies a vast, pitch-black frontier frozen in eternal silence. Beyond the orbit of Neptune, billions of miles away from the warmth of the Sun, the Kuiper Belt encircles our planetary system like a massive ring of cosmic ice. The Sun out here appears as a small but intensely bright disk, casting pale shadows across millions of ancient, frozen remnants left over from the birth of the solar system. This is not empty space. It is a vast, sparsely populated realm of icy worlds, dwarf planets, space rocks and primordial relics that hold the secrets to how our world came to be. Today we will learn about the Kuiper Belt, exploring its incredible scale, its strange inhabitants, and the hidden gravitational forces shaping the edge of our celestial backyard. Before we dive into the deep abyss of this frozen realm, please take a moment to like this video and subscribe to the channel so you never miss another deep dive into the mysteries of space. Also, let us know in the comments below where on Earth you are watching from and what time it is right now in your part of the world. Now, let us journey into the dark edge of the solar system. To truly understand the Kuiper Belt, we must first go back in time to an era when humanity believed the solar system ended abruptly at Pluto. For most of the 20th century, textbooks taught that our planetary neighborhood consisted of 9 planets, ending with a small, cold world discovered in 1930 by Clyde Tombaugh. Beyond Pluto lay nothing but an endless, empty void stretching across light years toward the nearest stars. However, a few visionary scientists refused to accept that nature would draw such an arbitrary line at the edge of the planetary kingdom. They began to wonder what might exist in the outer darkness, asking questions that would eventually reshape our understanding of cosmic history. The story of this realization begins with an Irish engineer and astronomer named Kenneth Edgeworth. In 1943, Edgeworth published a paper suggesting that the primeval material at the outer edge of the solar nebula was too widely scattered to coalesce into a single large planet. Instead, he proposed that thousands of smaller, icy bodies must have formed in this remote region beyond Neptune. Edgeworth argued that these tiny worlds remained scattered throughout the outer fringe, occasionally getting knocked out of their paths to travel toward the inner solar system as short-period comets. Despite the profound implications of his paper, Edgeworth's work was largely overlooked by the astronomical community at the time. A few years later, in 1951, the Dutch-born American astronomer Gerard Kuiper made a similar proposal, though with an interesting twist. Kuiper hypothesized that a disk of small, icy objects had indeed formed beyond Neptune during the early days of the solar system. However, Kuiper actually believed that this disk no longer existed. He theorized that Pluto was large enough to gravitationally scatter these smaller objects out into distant space over billions of years, leaving the region essentially empty. Irony would later claim a victory here, as the massive ring of icy worlds beyond Neptune would eventually bear Kuiper's name, despite his belief that it had vanished long ago. For decades, the ideas of Edgeworth and Kuiper remained theoretical speculations, buried under the weight of observational limitations. Telescopes in the middle of the 20th century were simply not powerful enough to detect tiny, faint objects billions of miles away, reflecting only a sliver of sunlight. Astronomers had no way of proving whether the region beyond Neptune was an empty wasteland or a thriving realm of ancient ice. The astronomical community treated the outer frontier as a settled topic, leaving Pluto standing alone in the dark. The tide began to turn in the late 1970s and 1980s, with the development of charge-coupled devices, or digital light sensors that could replace traditional glass photographic plates. These digital sensors were far more sensitive to light, allowing astronomers to capture faint celestial objects that had previously been completely invisible to human eyes. Around this time, a young British-born astronomer named David Jewitt became captivated by the mystery of the outer solar system. While working at the California Institute of Technology, Jewitt found himself puzzled by the massive gap in our knowledge. He could not accept that the solar system simply stopped at Pluto without any physical reason for such a sharp boundary. In 1987, Jewitt joined forces with Jane Liu, a graduate student from Vietnam studying at the Massachusetts Institute of Technology. Together, Jewitt and Liu embarked on what many of their peers considered a foolish and hopeless quest. they decided to search for objects beyond Pluto. They knew the odds were stacked heavily against them. Searching for a faint, slow-moving object in the vast expanse of the night sky was the astronomical equivalent of looking for a needle in 1,000 haystacks. Furthermore, telescope time at major observatories was fiercely competitive, and allocation committees were hesitant to give precious hours to a project that promised no guaranteed results. Undeterred by skepticism, Jewitt and Lou spent night after night at the Mauna Kea Observatory in Hawaii, using some of the most advanced optical telescopes in the world. Their method required painstaking precision. They would capture multiple images of the same patch of sky separated by a few hours, and then compare them, looking for any tiny speck of light that had moved against the backdrop of fixed background stars. Most objects in deep space stay perfectly still relative to one another, but an object orbiting our Sun beyond Neptune would show a subtle, characteristic drift over time. Year after year passed with no success. Night after night, Jewitt and Lou scanned thousands of digital images, only to find empty space, distant background galaxies, and familiar asteroids. By 1991, after 5 long years of searching without finding a single new object, frustration began to set in. Doubts lingered about whether Edgeworth and Kuiper had been wrong all along. Perhaps the region beyond Neptune really was an empty desert. Yet the duo persisted, driven by scientific curiosity and the belief that technological improvements in digital sensors would eventually give them the edge they needed. In August of 1992, their perseverance was finally rewarded. Jewitt and Lou were working at the 2.2-meter telescope on top of Mauna Kea, analysing digital images of a patch of sky in the constellation Pisces. Late into the night, as they compared consecutive images of the same field, they noticed a tiny, faint point of light moving at an extraordinarily slow pace. It was far too slow to be a nearby asteroid and far too faint to be a known planet. They carefully measured its motion over several hours and calculated its orbital speed. The math was unambiguous. This tiny speck of light was located roughly 44 astronomical units from the Sun, far beyond the orbit of Neptune and even further than Pluto was at that time. They had discovered an icy body about 250 kilometers in diameter, quietly orbiting in the deep darkness of space. Jewitt and Lou officially designated the object 1992 QB1. It was the first direct observational evidence that Gerard Kuiper and Kenneth Edgeworth were right about the existence of a vast reservoir of material at the edge of the planetary system. The discovery of 1992 QB1 shattered the long-held belief that Pluto was an isolated outlier at the end of the solar system. Instead, it proved that Pluto was merely the first known member of a colossal, previously undiscovered population of worlds. Just 6 months later, in the spring of 1993, Jewitt and Lou discovered a second object in the same region, designated 1993 FW. Within a few years, astronomers around the world joined the hunt, discovering dozens, then hundreds, and eventually thousands of similar icy bodies orbiting beyond Neptune. The realization swept through the scientific world like a tidal wave. Our solar system was vastly larger, richer, and more complex than anyone had ever imagined. This historic discovery transformed planetary science overnight. It initiated a gold rush of astronomical research focused on mapping this remote region, which was officially named the Kuiper Belt in honor of Gerard Kuiper. The discovery of 1992 QB1 proved that the solar system did not end with a lonely dwarf world, but rather opened up into a massive ring containing millions of frozen relics from the dawn of creation. The decades of stagnation were over, and a new era of cosmic exploration had officially begun. To truly understand why the Kuiper Belt exists in its present state, we must travel back over 4.5 billion years to the chaotic childhood of our solar system. The pristine, orderly arrangement of planets we observe today, moving in nearly circular orbits like clockwork, gives a deceptive impression of permanence. For a long time, classical astronomy assumed that the planets formed right where we see them now and remained in those exact orbits throughout cosmic history. However, modern astrophysics has revealed a far more dramatic and violent reality. The birth of our planetary neighbourhood was a tumultuous, chaotic struggle, defined by gravitational warfare, planetary scattering, and massive orbital migrations that completely reshaped the architecture of the outer solar system. At the centre of this evolutionary drama lies the NICE model, a groundbreaking theoretical framework developed in the early 2000s by an international team of scientists in Nice, France. According to this model, the early solar system looked radically different from its current configuration. Shortly after the primordial solar nebula cleared away, leaving behind the newly formed Sun, the giant planets were crammed into a much more compact arrangement. Jupiter, Saturn, Uranus, and Neptune all orbited much closer to the Sun than they do today, squeezed into a tight region between 5 and 15 astronomical units from our central star. Beyond the orbit of the outermost giant planet, which in some variations of the model was actually Uranus or Neptune before their positions swapped, existed a massive, dense disk of planetesimals. This primordial outer disk contained millions upon millions of icy, rocky, protoplanetary building blocks, boasting a collective mass between 20 and 30 times the mass of the Earth. The entire region was a teeming swarm of frozen worldlets composed of water ice, methane, ammonia, carbon monoxide, and rock, stretching out to roughly 30 astronomical units. Because these icy bodies were orbiting relatively close to the giant planets, gravitational interactions were frequent and intense. Tiny gravitational nudges began to cascade across millions of years. As the innermost giant planet, Jupiter, interacted with these icy planetesimals, its immense gravity flung many of them outward toward deep space. By Newton's third law of motion, every time Jupiter threw a planetesimal outward, Jupiter itself lost a fraction of an orbital degree and migrated slightly inward toward the Sun. Conversely, the outer giant planets, Saturn, Uranus, and Neptune, tended to throw these icy bodies inward toward Jupiter. In doing so, these outer giants gained orbital energy, causing their orbits to slowly expand outward, away from the Sun. For tens of millions of years, this process proceeded as a slow, gradual drift. The giant planets were steadily shifting their locations, inching through space as they exchanged orbital energy with trillions of icy fragments. Then, roughly 4 billion years ago, this gradual migration hit a catastrophic tipping point. Saturn had migrated outward to a critical distance where its orbital period matched exactly 2 orbits of Jupiter for every 1 orbit of Saturn. This phenomenon is known as an orbital resonance. Specifically, it was a 2-to-1 mean motion resonance. Every time Saturn completed 1 lap around the Sun, Jupiter completed precisely 2. This orbital alignment meant that Jupiter and Saturn were meeting at the exact same location in space repeatedly, amplifying their mutual gravitational pulls on one another, like someone pushing a child on a swing at just the right frequency. The gravitational feedback loop instantly destabilized the entire solar system. The orbits of Jupiter and Saturn became increasingly eccentric and stretched out, which in turn sent gravitational shockwaves tearing through the outer planetary realm. The delicate gravitational balance holding Uranus and Neptune was violently shattered. The 2 ice giants were hurled into wild, elongated, highly inclined orbits, plunging straight through the dense outer disk of icy planetesimals like bowling balls thrown into a rack of pins. Some versions of the NICE model even suggest that a 5th giant planet, an extra ice giant, was completely ejected from the solar system during this chaos, tossed into interstellar space as a rogue planet. As Uranus and Neptune ploughed through the primordial outer disk, they acted as cosmic snowplows on a planetary scale. Their immense gravity disrupted the orbits of trillions of icy objects simultaneously. A massive fraction of the outer disk was violently scattered in all directions. Millions of icy bodies were hurled inward toward the inner solar system, triggering a ferocious period of intense asteroid and comet impacts across the terrestrial worlds known as the Late Heavy Bombardment. Scars from this violent epoch remain etched onto the cratered surfaces of the Moon, Mercury, and Mars to this day. While countless icy bodies were driven inward or hurled completely out of the solar system into interstellar space, a vast quantity of material was flung outward into higher, distant orbits. The moving gravitational fields of the migrating ice giants acted as a slingshot, clearing out over 99% of the total mass of the original outer disk. The tiny fraction of material that survived this dynamic clearance was pushed into a region where the gravitational influence of the planets weakened just enough for orbits to stabilize over billions of years. This surviving residue, the remaining 1% of the original primordial protoplanetary disk, became the Kuiper Belt. Neptune slowly settled into its current nearly circular orbit at 30 astronomical units from the Sun, where its gravitational grip established a sharp boundary. The region immediately beyond Neptune became a dynamic gravitational harbour. Objects that were pushed into specific resonant orbits with Neptune managed to survive, while others were scattered into eccentric paths forming the scattered disk. The consequence of this ancient planetary migration is that the modern Kuiper Belt is essentially a fossilized graveyard of the early solar system. It represents the outer edge of the original planet-forming disk that was violently swept, thinned out, and reshaped by the migration of the giant planets. Without the chaotic orbital dance of Jupiter, Saturn, Uranus and Neptune, the Kuiper Belt would be a far denser, much heavier belt of planetary building blocks that might have eventually coalesced into a fifth giant planet. Instead, what remains today is a vast, cold, diffuse ring of frozen debris, preserved in the deep freeze of space. The chemical composition of the Kuiper Belt object reflects the pristine ingredients that existed in the solar nebula before the Sun ignited its nuclear furnace. Because these objects were tossed out to distances where solar radiation is extremely faint, they have remained practically unaltered for over 4 billion years. Understanding the Nice model and the chaotic origin of the Kuiper Belt provides planetary scientists with a powerful framework for deciphering not only our own solar system, but also exoplanetary systems across the galaxy. We now observe distant stars surrounded by massive dust rings and migrating giant planets, proving that gravitational chaos is a universal feature of planetary formation. The Kuiper Belt stands as the ultimate witness to this violent history, a frozen testament to the chaotic dance of giant worlds that shaped the solar system we inhabit today. Beyond the orbit of Neptune, in the dark and frigid expanses of the Kuiper Belt, lies a realm dominated by a fascinating class of celestial bodies known as dwarf planets. For generations, humanity recognized this region as the domain of a single, mysterious world named Pluto. Discovered in 1930 by Clyde Tombaugh at the Lowell Observatory in Arizona, Pluto captured the imagination of the world as the mysterious ninth planet of our solar system. For 76 years, textbooks around the globe taught schoolchildren that Pluto stood alongside giant worlds like Jupiter and terrestrial spheres like Earth as a full member of the planetary family. However, the discovery of the Kuiper Belt and the subsequent identification of other massive icy bodies in the early 2000s permanently altered our understanding of what Pluto represents, triggering one of the most intense and passionate scientific debates in modern history. To understand the nature of Pluto, one must look closely at its physical structure, its complex environment, and its dynamic relationship with its largest moon, Charon. Pluto orbits the Sun at an average distance of roughly 39.5 astronomical units, taking approximately 248 Earth years to complete a single journey around our central star. Its orbit is remarkably eccentric and tilted, inclined at more than 17 degrees relative to the orbital plane of the major planets. At its closest approach, or perihelion, Pluto actually dips inside the orbit of Neptune, coming closer to the Sun than the ice giant itself for 20 years out of every orbit. Yet, due to a stable 3-2 orbital resonance with Neptune, the two worlds will never collide, as Pluto completes exactly 2 orbits around the Sun for every 3 orbits completed by Neptune. In terms of physical composition, Pluto is a cold, complex world, composed primarily of nitrogen ice, methane ice, carbon monoxide ice, and water ice, surrounding a dense rocky core. With a diameter of roughly 2,377 kilometers, Pluto is smaller than Earth's moon, yet it possesses a surprisingly dynamic geology. Data from space missions and ground-based observations have revealed sweeping plains of frozen nitrogen, vast mountain ranges composed of rock-hard water ice, and complex organic compounds called Tholins that give its surface a distinct reddish-brown hue. Furthermore, Pluto harbours a tenuous seasonal atmosphere composed mainly of nitrogen, methane, and carbon monoxide. As Pluto approaches the Sun along its elliptical path, these surface ice layers sublimate directly into gas, creating an atmospheric envelope. As Pluto moves further away into the deep freeze of space, this atmosphere cools, collapses, and freezes back onto the surface as frost. Pluto does not exist in isolation. It is part of a binary system with its giant satellite, Charon. Discovered in 1978 by astronomer James Christie, Charon is so large relative to Pluto, possessing roughly half the diameter and 1/8 the mass of Pluto, that the centre of mass of the two bodies lies in the open space between them. This means that Pluto and Charon actually orbit a shared balance point outside of Pluto's physical body, making them a true double dwarf planet system. Both worlds are tidally locked to one another, showing the exact same face to each other continuously as they spin in a synchronization dance that lasts 6.4 Earth days. Later discoveries showed that Pluto also possesses 4 smaller moons, named Styx, Nix, Kerberos, and Hydra, which move in chaotic, tumbling orbits around the central binary pair. For decades, Pluto reigned supreme as the undisputed king of the outer solar system. Because it was the only object known in that remote region for over 60 years, astronomers assumed it was a unique, isolated world. However, as digital light sensors and large sky survey telescopes advanced in the late 1990s and early 2000s, scientists began detecting other sizable objects in the Kuiper Belt. The illusion of Pluto's solitary status began to crumble, setting the stage for a dramatic astronomical showdown. The catalyst for this scientific revolution arrived in January of 2005, when a team of astronomers led by Mike Brown at the California Institute of Technology, Chad Trujillo at the Gemini Observatory, and David Rabinowitz at Yale University discovered a faint, slow-moving object in images captured at the Palomar Observatory in California. This object, initially designated 2003 UB 313, was located at an astonishing distance of nearly 97 astronomical units from the Sun, nearly 3 times further away than Pluto. The discovery team spent months analysing orbital data and thermal measurements to determine the size of this distant world. Initial measurements suggested that this newly discovered body was not only larger in diameter than Pluto, but also significantly more massive. The announcement sent shockwaves through the scientific community and the media. News outlets declared that a 10th planet had been found in the outer darkness of the solar system. The discovery team informally nicknamed the object Xena after a famous television warrior princess, while its satellite was given the temporary nickname Gabrielle. The discovery of an object larger and more massive than Pluto created an immediate logical crisis for the astronomical community. If Pluto was considered a planet, then this newly discovered object must also be recognized as the 10th planet. Furthermore, astronomical surveys were rapidly finding other massive icy worlds beyond Neptune, such as Quaoar and Haumea. Scientists realized that if the definition of a planet remained unchanged, the solar system would soon boast dozens or even hundreds of planets as telescope technologies continued to improve. Alternatively, astronomers had to confront an uncomfortable possibility. Perhaps Pluto was not a true planet at all, but simply one of the largest members of a newly discovered population of icy debris. The tension reached a breaking point in August of 2006 at the General Assembly of the International Astronomical Union, held in Prague, Czech Republic. Hundreds of astronomers gathered to debate and formalize a rigorous scientific definition of the word planet. Up to that point, the term planet had never been officially defined by modern science. It was an informal, historical concept inherited from ancient Greek terminology meaning wanderer. The debate in Prague was fierce and highly contentious. One group of scientists argued that any object large enough for its own gravity to crush it into a spherical shape should be classified as a planet, a definition that would have kept Pluto and added several new worlds to the solar lineup. However, another group of dynamicists argued that physical shape alone was insufficient. They contended that a true planet must dominate its orbital environment through immense gravitational power. On August 24, 2006, the International Astronomical Union voted on a landmark resolution that established 3 official criteria for an object to be designated a planet within our solar system. To be classified as a planet, a celestial body must meet 3 specific conditions. First, it must be in orbit around the Sun. Second, it must have sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium or nearly round shape. And third, it must have cleared the neighbourhood around its orbit. It was this third criterion that dramatically changed planetary science. To clear its neighbourhood, a world must be gravitationally dominant in its region of space, meaning it has either swept up, flung away, or gravitationally controlled almost all other debris sharing its orbital zone. While major planets like Earth, Jupiter and Neptune represent over 99% of the total mass in their respective orbital zones, Pluto accounts for only a tiny fraction of the total mass in its region, sharing its neighbourhood with hundreds of thousands of other icy objects in the Kuiper Belt. Because Pluto failed to meet the third criterion, it was stripped of its planet status and reassigned to a newly created category called dwarf planets. A dwarf planet was defined as a body that orbits the Sun, has sufficient self-gravity to achieve a nearly round shape, has not cleared its orbital neighbourhood, and is not a natural satellite. Under this new classification system, Pluto was officially assigned the minor planet catalogue number 134340. Joining Pluto in this new category was the object that sparked the revolution in the first place, which was officially named Eris, after the ancient Greek goddess of discord and strife, a fitting title given the chaotic scientific debate its discovery had unleashed. Eris's satellite was officially named Dysnomia, after the goddess of lawlessness. Subsequent observations by space telescopes and high-resolution instruments refined the measurements of Eris. While Pluto was eventually determined to be slightly larger in physical diameter than Eris, by a margin of about 40 kilometers, Eris was proven to be roughly 27% more massive than Pluto. Eris is an extraordinarily dense, reflective world covered in a highly brilliant layer of methane frost, reflecting nearly 96% of the light that hits its surface. Its extreme density suggests a predominantly rocky interior covered by a thin skin of bright ice. The reclassification of Pluto and the discovery of Eris sparked widespread public outrage and intense debate within the scientific community that continues to linger in popular culture. Many members of the public felt a deep emotional connection to Pluto, viewing its demotion as an unfair rejection of a beloved world. However, among planetary scientists, the creation of the dwarf planet category was widely recognized as a major scientific victory. It reflected a modern, mature understanding of the structure and evolution of our solar system. Pluto and Eris are not defective planets. Rather, they are premier representatives of a vast, ancient and dynamically fascinating region that dwarf planets call home. The demotion of Pluto was not a loss of status, but a gain in context. Pluto was transformed from an anomalous, tiny planetary outcast at the edge of the map into the proud ambassador of a vast, frozen frontier that holds the untamed history of our cosmic origin. While Pluto and Eris dominated headlines during the reshaping of our cosmic map, the Kuiper Belt and its outlying regions harbour several other fascinating worlds that defy simple categorization. These distant realms challenge our understanding of planetary physics, rotational dynamics, and orbital evolution. Among these remarkable inhabitants, 3 worlds stand out for their bizarre physical characteristics and perplexing paths through space. Haumea, the fast-spinning triaxial ellipsoid; Makemake, a brilliant world of frozen hydrocarbons; and Sedna, a mysterious nomad travelling through the deepest abyss of our solar system. Located at an average distance of roughly 43 astronomical units from the Sun, Haumea is arguably one of the most unusual objects in the entire planetary lineup. Discovered in late 2004 by observation teams monitoring the outer solar system, this dwarf planet immediately caught the attention of astrophysicists due to its extremely rapid rotation and strange, elongated shape. While Earth takes 24 hours to complete a single spin on its axis, Haumea completes a full rotation in just under 4 hours. This makes Haumea the fastest rotating large body known in the solar system. This hyperrotation generates immense centrifugal force, which actively resists the pull of gravity trying to draw the world into a perfect sphere. As a direct consequence of this furious spinning, Haumea has been stretched out into an elongated egg-like shape known scientifically as a triaxial ellipsoid. Its longest axis measures approximately 2,300 kilometers across, comparable in length to Pluto, while its shortest axis spans only about 1,000 kilometers. If you were to look at Haumea from space, it would resemble a giant, gleaming cosmic football tumbling continuously through the dark. The extreme rotation rate of Haumea is not an accident of creation, but rather the dramatic signature of an ancient catastrophic collision. Billions of years ago, during the early chaotic era of planetary migration, a massive icy impactor struck the primordial progenitor of Haumea at a high velocity. This glancing blow spun Haumea up to its present frantic rotational velocity and shattered a large portion of its original outer icy mantle. The debris from this violent collision was blasted into space, forming a swarm of icy fragments that continue to share similar orbital paths around the Sun. This group of fragments represents the only known collisional family in the Kuiper Belt. Among the remnants left behind by this ancient impact are Haumea's two natural satellites, Hiaka and Namaka, named after the mythological daughters of the Hawaiian volcano goddess. Furthermore, detailed observations conducted in 2017 during a stellar occultation, when Haumea passed directly in front of a distant background star, revealed an even more surprising feature. Haumea possesses a dense, narrow ring system orbiting around its equator. Measuring roughly 70 kilometers in width and positioned thousands of kilometers above its surface, this ring makes Haumea the first dwarf planet and the most distant object in the solar system known to harbor a ring system. In terms of surface composition, Haumea is coated in a brilliant veneer of almost pure, crystalline water ice. Under ordinary circumstances, in the deep freeze of the outer solar system, water ice becomes amorphous due to continuous bombardment by high-energy cosmic rays and solar radiation. Crystalline ice requires an energy source to maintain its ordered molecular lattice, suggesting that internal heating processes, such as the decay of radioactive elements or tidal forces, may be driving cryovolcanic activity that resurfaces Haumea with freshwater ice over time. Moving further through the Kuiper Belt, we encounter Makemake, officially designated as the third recognized dwarf planet beyond Neptune. Discovered in March of 2005 by the same research team responsible for Eris and Haumea, Makemake was found orbiting at an average distance of roughly 45 astronomical units from the Sun. Named after the creator deity of the Rapa Nui people of Easter Island, Makemake is slightly smaller than Pluto and Eris, with an estimated diameter of approximately 1,430 kilometers. Makemake appears visually as a deep, luminous reddish object in space. Its high surface reflectivity, or albedo, indicates that its frozen terrain is covered by an ultra-clean layer of compressed methane ice, mixed with trace amounts of ethane and nitrogen. So, solar ultraviolet light continuously breaks down these simple hydrocarbons, driving complex chemical reactions that produce complex organic polymers called tholins. These tholins accumulate on the frozen surface, imparting a distinct reddish tint, similar to the colored terrains of Pluto. Unlike Pluto, which possesses a complex atmosphere, Makemake presents an intriguing atmospheric puzzle. For many years, scientists believed Makemake might host a similar seasonal atmosphere that expands near perihelion and collapses as the world retreats into deep space. However, high-precision stellar occultation measurements revealed that Makemake lacks a widespread global atmosphere. Instead, its atmospheric vapor appears to be confined locally over warmer, dark patches of terrain, while the vast methane ice sheets remain cold and inert. For over a decade after its discovery, Makemake appeared to be a completely solitary world, devoid of any natural satellites. This absence posed a challenge for planetary scientists, as measuring the orbital path of a moon provides the most accurate method for calculating the total mass and density of a celestial body. However, in 2016, images captured by the Hubble Space Telescope revealed a tiny faint moon orbiting Makemake at a distance of roughly 21,000 kilometers. Nicknamed MK2 by the Discovery team, this small satellite is extremely dark, reflecting very little sunlight compared to its brilliant parent world. The discovery of MK2 enabled astronomers to precisely calculate Makemake's density, confirming that it possesses a solid rocky core enveloped by a thick outer mantle of ice. While Haumea and Makemake reside within the main realm of the Kuiper Belt, there exists another class of extreme worlds that travel far beyond the traditional boundaries of the belt. The premier representative of these extreme worlds is Sedna, officially designated as 2003 VB12. Discovered in November of 2003, Sedna orbits at such immense distances from the Sun that it defies traditional classification, serving as a dynamic bridge between the Kuiper Belt and the theoretical inner boundary of the distant Oort cloud. Sedna follows an extraordinarily elongated, eccentric orbit that takes approximately 11,400 years to complete a single revolution around the Sun. At its closest approach, or perihelion, Sedna remains a staggering 76 astronomical units away from the Sun, far beyond the orbit of Neptune and the outer boundary of the classical Kuiper Belt. At its furthest point, or aphelion, Sedna travels out to a breathtaking distance of nearly 937 astronomical units, plunging deep into the frozen darkness where the Sun appears as nothing more than an intensely bright point of light in an endless black sky. Measuring roughly 1,000 kilometers in diameter, Sedna is one of the reddest objects in the entire solar system, almost matching the intense coloration of Mars. Spectroscopic analysis indicates that its surface is a mixture of water ice, methane ice, nitrogen ice, and complex organic tholins. Because it remains so far from the Sun throughout its multi-millennial orbit, Sedna's surface temperature never rises above 35 Kelvin, preserving its primordial chemical composition in an uninterrupted deep freeze since the formation of the solar system. The fundamental mystery surrounding Sedna lies in its unusual orbit. Classical Kuiper Belt objects are gravitationally influenced by Neptune, which shapes their paths through mean motion resonances or scattering events. However, Sedna's perihelion is so distant from Neptune's orbit that the ice giant could not possibly have nudged Sedna into its current path. Furthermore, Sedna never comes close enough to the giant inner planets to have been scattered by them, nor is it far enough out to be easily disrupted by the gravitational tides of passing neighbor stars in the modern galactic environment. To explain how an object like Sedna reached such an isolated, highly eccentric orbit, astrophysicists have proposed several compelling hypotheses. One major theory suggests that Sedna was detached from the main planetary disk during the infancy of the solar system, when the Sun was still embedded in its birth cluster alongside hundreds of neighboring stars. Close gravitational flybys from sibling stars in that dense stellar nursery could have lifted Sedna's orbit away from Neptune, leaving it permanently locked in a distant, isolated realm. Another hypothesis suggests that Sedna was not originally native to our solar system at all, but was instead captured from the outer disk of a passing neighboring star during an ancient stellar encounter. A third highly intriguing possibility is that Sedna's path is being actively manipulated by the gravitational pull of an undiscovered massive planet lurking in the dark outer fringes of our planetary system, a hypothetical world often referred to as Planet 9. Together, Haumea, Makemake and Sedna illustrate the astonishing diversity of worlds populating the outer frontier. From fast-spinning ringed ellipsoids forged in cosmic collisions to luminous hydrocarbon worlds and distant, isolated nomads wandering through the outer void, these dwarf planets demonstrate that the solar system beyond Neptune is not a uniform wasteland, but a complex, dynamically rich laboratory of planetary evolution. To truly understand the complex dynamics of the Kuiper Belt, astronomers cannot simply view it as a uniform, chaotic ring of icy debris drifting randomly around the Sun. Instead, decades of precision telescope observations and orbital mapping have revealed a highly organized cosmic ecosystem. The millions of frozen bodies inhabiting this distant frontier are categorized into distinct dynamical families, each defined by its unique orbital shape, inclination, and gravitational relationship with the giant planet Neptune. By analyzing these orbital characteristics, planetary scientists can classify the inhabitants of the outer solar system into three primary populations: the classical Kuiper Belt objects, the resonant Kuiper Belt objects, and the scattered disk objects. The first major group consists of the classical Kuiper Belt objects, often referred to informally by astronomers as Cubewanos. This unusual name traces its history back to the very first object discovered beyond Pluto in 1992, which was designated 1992 QB1. Objects that share similar orbital properties to this groundbreaking discovery were initially referred to as QB10s, which eventually evolved into the scientific term Cubewanos. These classical objects reside primarily in the core region of the belt, located between roughly 42 and 48 astronomical units from the Sun. What defines the classical population is its dynamic independence from Neptune. Unlike other families in the outer solar system, classical objects move along relatively stable, nearly circular orbits with low eccentricities, keeping them safely beyond the gravitational reach of Neptune at all times. They have remained largely undisturbed since the birth of the solar system, serving as the most pristine planetary building blocks surviving in their original birthplace. Within the classical population, astronomers further divide objects into two distinct subgroups based on their orbital tilt, or inclination, relative to the main plane of the solar system. The first subgroup is the dynamically cold classical population. Despite the word cold, this term does not refer to surface temperature, but rather to the low orbital energy and calm trajectories of these bodies. Cold classical objects have orbital inclinations of less than 5 degrees, moving in smooth, flat orbits within the ecliptic plane. Such rockscopic analysis reveals that cold classical objects possess a distinct, uniform reddish color and high surface albedo, indicating that they formed in place and have never been disrupted by major gravitational shocks or chaotic migrations. The second subgroup is the dynamically hot classical population. These objects possess significantly higher orbital inclinations, sometimes tilted more than 30 degrees relative to the ecliptic plane, as well as higher eccentricities. The term hot refers to their high orbital energy and excited paths through space. Hot classical objects exhibit a wider variety of colors, ranging from neutral grey to deep red, which suggests that they originally formed much closer to the Sun in different chemical environments before being violently tossed outward into the classical region during the planetary migration epoch described by the NICE model. The second primary population of the outer frontier consists of the resonant Kuiper Belt objects. Unlike classical objects, which actively avoid gravitational interactions with Neptune, resonant objects are fundamentally defined by their intimate, locked gravitational relationship with the ice giant. A mean motion resonance occurs when the orbital period of an icy body and the orbital period of Neptune form a simple integer ratio. This mathematical locking ensures that the two bodies regularly meet at fixed relative positions in space, creating a recurring cycle of gravitational interactions that stabilizes the smaller object's path over billions of years. The most famous and heavily populated resonant group is the 3-2 orbital resonance, whose members are affectionately known as Plutinos, meaning little Plutos. For every 3 orbits Neptune completes around the Sun, a Plutino completes precisely 2 orbits. Pluto itself is the largest member and namesake of this dynamical family. Because of this 3-2 mathematical relationship, even though Plutinos cross inside the orbital radius of Neptune during their closest approach to the Sun, they are always located at safe, distant points along their orbit whenever Neptune passes near their orbital longitude. This gravitational harmony prevents them from ever colliding with or being scattered away by the giant planet. Plutinos make up a massive fraction of the total known population of the Kuiper Belt, accounting for roughly 20% of all catalogued objects in the region. Their orbits tend to be moderately eccentric and inclined, reflecting the ancient history when an outward migrating Neptune swept through the primordial disk, capturing millions of icy planetesimals into its resonant gravitational traps like a sweeping net. Beyond the Plutinos, Neptune controls several other distinct resonant populations that inhabit different zones of the belt. One notable family is the 2-1 resonance, situated near the outer edge of the classical belt around 47.5 astronomical units. Objects in this group complete 1 orbit around the Sun for every 2 orbits completed by Neptune and are commonly referred to as Plutinos.
Other recognized resonant families include the 5-2 resonance, the 4-3 resonance, and the 5-3 resonance.
Each of these resonant families serves as a gravitational fossil, recording the precise speed, distance, and direction of Neptune's ancient planetary migration through the early solar system. The third primary group of outer inhabitants consists of the scattered disk objects.
While classical objects enjoy stable, circular paths,
and resonant objects navigate locked, harmonious orbits, scattered disk objects live in a dynamic state of extreme chaos and instability. The scattered disk overlaps with the Kuiper Belt, but extends much further out into the frozen abyss, stretching from roughly 35 astronomical units at its inner boundary to hundreds or even thousands of astronomical units at its furthest reaches. Scattered disk objects are defined by their highly eccentric, elongated orbits and extreme orbital inclinations. Many of these bodies follow paths that are tilted at angles exceeding 40 or 50 degrees relative to the planetary plane. Their closest approach to the Sun, or perihelion, typically brings them within 30 to 35 astronomical units, placing them dangerously close to the gravitational sphere of influence of Neptune. The origin of the scattered disk is rooted in violent gravitational encounters. Billions of years ago, these icy bodies were originally classical or resonant planetesimals that strayed too close to Neptune. The immense gravity of the ice giant acted as a celestial catapult, violently scattering them into wild, stretched-out trajectories. Because their perihelia remain tucked close to Neptune's orbit, scattered disk objects continue to experience periodic gravitational nudges from the planet every time they return to the inner portion of their paths. Over long astronomical timescales, these recurring gravitational perturbations cause their orbits to continuously evolve, shifting their aphelia further into space or altering their inclinations. The most famous representative of the scattered disk population is the dwarf planet Eris, whose discovery ignited the debate over the definition of a planet. Eris travels along a highly eccentric path that takes it from a perihelion of 37 astronomical units out to an aphelion of nearly 98 astronomical units, inclined at a steep angle of 44 degrees. Other large scattered disk objects include Gong and several other distant trans-Neptunian worlds, which showcase the extreme physical and dynamical diversity of this chaotic region. In addition to serving as a fascinating realm of study in its own right, the scattered disk plays a critical role in the ongoing life cycle of our planetary system. Because its orbits are dynamically unstable, scattered disk objects are frequently nudged into new trajectories that send them plunging inward toward the inner planets, transforming them into centaurs and short-period comets that light up our night skies. By dissecting the outer solar system into classical Cubewanos, resonant Plutinos and Plutinos, and chaotic scattered disk objects, planetary scientists can read the dynamic history of our cosmic neighborhood like a book. Each family tells a specific chapter of the same grand epic, revealing how the gravitational choreography of giant planets swept, locked, and scattered trillions of primordial icy worldlets into the highly structured frontier we observe today. For billions of years, humanity viewed comets with a mixture of awe, dread, and fascination, appearing unpredictably as luminous spectres in the night sky, drawing long, glowing tails behind them. These celestial visitors were historically interpreted as omens of doom, war, or royal deaths. Modern astrophysics, however, has transformed our understanding of these mysterious wanderers. Rather than cosmic heralds of misfortune, comets are now recognized as icy time capsules preserved from the dawn of creation. Far more intriguing is the realization that the Kuiper Belt serves as the primary reservoir for a vast class of these icy travelers, and that their ancient bombardments of the young Earth may have delivered the fundamental ingredients necessary for the origin and evolution of life itself. To understand the connection between the Kuiper Belt and comets, one must first distinguish between the two primary categories of comets that visit the inner solar system: long-period comets and short-period comets. This distinction is defined by their orbital periods, their trajectories through space, and their distinct cosmic places of origin. Long-period comets are celestial bodies that take anywhere from 200 years to several million years to complete a single orbit around the Sun. Their paths are wildly unpredictable, entering the inner planetary realm from random directions across three-dimensional space, often inclined at steep angles to the plane of the planets. These long-period wanderers originate in the Oort cloud, a theoretical giant spherical shell of icy debris that completely surrounds the solar system at immense distances, extending from roughly 2,000 to over 100,000 astronomical units from the Sun. The Oort cloud is so distant that its outer limits reach nearly halfway to the nearest neighbouring star system, Proxima Centauri, where the gravitational hold of our Sun becomes extremely weak. In stark contrast, short-period comets, also known as periodic comets, complete their journeys around the Sun in less than 200 years, with many taking only a decade or two. Curiously, these comets travel along predictable, low-inclination orbits that closely align with the flat plane where Earth and the major planets reside. The low orbital tilt and predictable cycles of short-period comets pointed planetary scientists directly toward a flattened, disk-like reservoir beyond Neptune, the Kuiper Belt, and its dynamically chaotic offspring, the scattered disk. The mechanism that transforms a frozen, dormant Kuiper Belt object into a brilliant, short-period comet is a multi-stage gravitational pipeline. Millions of icy objects in the Kuiper Belt drift quietly in the deep freeze of space, billions of miles away from the Sun. However, subtle gravitational interactions, such as a close encounter between two icy bodies, a nudge from the resonant pull of Neptune, or perturbations from passing galactic tides, can nudge an object out of its stable orbit. Once an icy body loses its orbital stability, it begins to fall inward toward the giant planets. As it crosses the orbits of Neptune, Uranus, Saturn and Jupiter, it enters a transitional class of celestial bodies known as centaurs, named after the mythological creatures that were half human and half horse. Centaurs possess a dual nature, exhibiting characteristics of both asteroids and comets. Centaurs follow wild, highly chaotic orbits that cross the paths of the giant planets. Gravitational interactions with Jupiter eventually act as a gravitational slingshot, hurling these centaurs into the inner solar system. As a centaur plunges past the orbit of Mars and approaches the Sun, the dramatic increase in solar radiation triggers a profound transformation. In the deep freeze of the Kuiper Belt, surface temperatures remain only a few tens of kelvins above absolute zero, keeping volatile compounds frozen solid. But as the object moves closer than roughly 3 to 5 astronomical units from the Sun, solar heat penetrates its frozen crust. Water ice, carbon dioxide, methane and ammonia begin to sublimate directly from solid ice into gas, skipping the liquid phase entirely. This rapid expansion of escaping gas vents violently into space, carrying fine dust particles away from the nucleus. The expanding gas and illuminated dust form a colossal, luminous atmosphere surrounding the nucleus, known as a coma, which can expand to become larger than the Earth. As the comet continues to speed toward the Sun, solar radiation pressure and the energetic solar wind push these escaping gas ions and dust particles away from the Sun, crafting two magnificent, distinct tails that stretch across tens of millions of miles. A bluish ion gas tail pointing directly away from the Sun along magnetic field lines, and a curving white dust tail along the comet's trajectory. While the dramatic display of a comet in the night sky is visually stunning, its chemical composition carries far deeper scientific significance. Comets originating from the Kuiper Belt are essentially frozen chemical vaults that have preserved the pristine primordial recipe of our solar nebula for over 4.5 billion years. By analysing the light emitted by cometary comas and conducting direct space probe missions, scientists have determined that comets are composed of water ice, frozen carbon monoxide, methane, ammonia, complex silicates, and a rich array of organic molecules. This chemical inventory lies at the heart of one of the most fundamental questions in modern science. How did Earth transform from a hot, barren, molten rock after its formation into a vibrant, ocean-covered world teeming with life? During the early assembly of the Earth, intense heat from accretion and radioactive decay, combined with catastrophic impacts such as the collision that formed the Moon, drove off any primordial water and atmospheric gases.
The early Earth was left as a dry, sterile sphere of molten rock. To explain the subsequent appearance of sprawling oceans and dynamic atmospheres, geophysicists developed the theory of late veneer, or external delivery. According to this hypothesis, during the violent era of planetary migration known as the Late Heavy Bombardment, trillions of icy bodies were hurled inward from the collapsing outer disk and the newly formed Kuiper Belt. For hundreds of millions of years, a relentless rain of comets and icy planetesimals slammed into the young Earth. For a long time, scientists debated whether comets were the primary source of Earth's ocean water. The key to testing this hypothesis lies in measuring the deuterium to hydrogen ratio in water. Deuterium, often called heavy hydrogen, is an isotope of hydrogen containing a neutron alongside its proton. Water molecules containing deuterium have distinct chemical signatures. If Earth's ocean water was delivered by comets, the ratio of deuterium to hydrogen in cometary ice should match the precise signature found in Earth's oceans today. Measurements conducted by space probes, such as the European Space Agency's Rosetta mission to Comet 67P, revealed that some comets possess a higher deuterium to hydrogen ratio than Earth's oceans. However, high-precision observations of other short-period comets originating from the Kuiper Belt, such as Comet Hartley 2, revealed a deuterium to hydrogen ratio that matches Earth's ocean water almost perfectly. These measurements show that cometary water is chemically diverse. Some short-period comets have Earth-like isotopic ratios, while others do not, so the relative contributions of comets and asteroids to Earth's oceans remain actively debated. Even more profound than the delivery of liquid water is the realization that Kuiper Belt objects delivered the fundamental organic building blocks of life itself. Life as we know it requires complex organic compounds based on carbon, nitrogen, hydrogen, and oxygen, including amino acids, which serve as the building blocks of proteins, and nucleobases, which form the structural framework of genetic code, such as RNA and DNA. Laboratory experiments mimicking the deep space environment of the Kuiper Belt have demonstrated that when simple icy mixtures of water, methane, ammonia, and carbon monoxide are exposed to ultraviolet radiation and cosmic rays at ultra-cold temperatures, complex chemical synthesis occurs automatically. Simple molecules bind together to form complex organic compounds, including amino acids, sugars, and polycyclic aromatic hydrocarbons. When space missions like NASA's Stardust mission captured dust samples from Comet Wild 2, a short-period comet originating from the Kuiper Belt, and brought them back to Earth, laboratory analysis confirmed the presence of the amino acid glycine alongside a complex cocktail of nitrogen-bearing organic molecules. Furthermore, data from the Rosetta spacecraft detected a rich variety of organic molecules on Comet 67P, including glycine, methylamine, ethylamine, and phosphorus, an essential element required for the backbone of DNA and cell membranes. This discovery provides a breathtaking perspective on our cosmic origins. The icy worlds drifting in the dark, frozen expanse of the Kuiper Belt are not distant, irrelevant rocks isolated from our living world. Instead, they represent the original nurseries that forged the essential chemical recipe for life. Billions of years ago, when the giant planets reshaped the solar system, these frozen time capsules were hurled into the inner solar realm, raining down onto the primordial Earth. It is possible that some of the water and organic material found on Earth was delivered by icy bodies from the outer solar system, including populations dynamically connected to the Kuiper Belt. Organ molecules preserved in outer solar system bodies, they have contributed useful ingredients to prebiotic chemistry on the young Earth. The Kuiper Belt is not merely a distant graveyard of icy debris. It is the ultimate cosmic cradle, preserving the ancient seeds of life that transformed Earth into a living world. For decades, humanity's knowledge of the far reaches of the solar system was confined to fuzzy images captured by ground-based observatories and orbital space instruments. Even the most powerful images taken by the Hubble Space Telescope rendered Pluto as little more than a blurry, pixelated smudge of light, an enigmatic world holding its secrets behind billions of miles of empty space. All of that changed on January 19, 2006, when the National Aeronautics and Space Administration launched a small robotic spacecraft named New Horizons from Cape Canaveral, Florida. Weighing only about 1,000 pounds and roughly the size of a grand piano, New Horizons embarked on an unprecedented, daring journey across the vast expanse of our solar neighbourhood, bound for the unexplored frontier of Pluto and the Kuiper Belt. To reach its distant target within a reasonable time frame, New Horizons was launched atop a powerful Atlas V rocket equipped with solid rocket boosters, becoming the fastest man-made object ever launched from Earth at that time. Leaving Earth at a staggering velocity of over 36,000 miles per hour, the probe crossed the orbit of the Moon in just 9 hours, a journey that had taken Apollo astronauts 3 days. Just over a year later, in February 2007, New Horizons reached Jupiter. The spacecraft executed a precision gravity assist maneuver, using the immense gravitational pull of the gas giant to slingshot itself toward the outer solar system, gaining an extra 9,000 miles per hour in speed and cutting its transit time to Pluto by nearly 4 years. Following its close encounter with Jupiter, New Horizons entered an extended period of electronic hibernation to preserve its onboard systems and instrument life. For 8 long years, the probe drifted quietly through the cold void, waking once a year for routine system checks and calibration. Inside its small chassis sat a suite of 7 sophisticated scientific instruments designed to map geology, analyze surface composition, measure atmospheric structure, and search for magnetospheres and moons. Powered by a single radioisotope thermoelectric generator utilizing decaying plutonium-238, New Horizons relied on nuclear heat to function in a realm where solar power is entirely useless. In December 2014, after travelling more than 3 billion miles over nearly 9 years, New Horizons woke permanently from hibernation. In January 2015, its instruments turned toward Pluto, and the spacecraft began its long-awaited flyby approach. The engineering challenges of this encounter were immense. Because radio signals travelling at the speed of light take over 4.5 hours to travel one way between Pluto and Earth, real-time control was impossible. Every command sequence had to be pre-programmed months in advance. Furthermore, because Pluto has an extremely faint gravitational hold compared to gas giants, New Horizons could not easily slow down to enter orbit without carrying an impossible amount of fuel. It had only one shot, flying past Pluto at a relative speed of nearly 31,000 miles per hour. On July 14, 2015, New Horizons made its closest approach, zooming just 7,700 miles above the frozen surface of Pluto. The data transmitted back to Earth over the following months utterly shattered the scientific community's expectations. Planetary scientists had anticipated a dead, heavily cratered world frozen solid since the dawn of the solar system. Instead, New Horizons revealed a remarkably young, geologically active world featuring sweeping plains, towering mountain ranges, exotic weather cycles, and complex chemical processes. The most iconic discovery was a vast, bright, heart-shaped feature, officially named Tombau Regio, in honor of Pluto's discoverer. The western lobe of this immense heart is a colossal bright plain known as Sputnik Planitia. Spanning roughly 1,000 kilometers across, Sputnik Planitia is a smooth, cell-like plain composed entirely of frozen nitrogen, carbon monoxide, and methane ice. Incredibly, this vast plain is completely devoid of impact craters, indicating that its surface is extraordinarily young in geological terms, likely less than 100 million years old. High-resolution imaging revealed that Sputnik Planitia is divided into irregular polygonal cells bounded by subtle troughs. Scientific analysis confirmed that these cells are driven by active solid-state thermal convection. Heat rising slowly from deep within Pluto's interior warms the lower layers of nitrogen ice, causing them to become buoyant and rise slowly to the surface in vast, slow-moving, overturned cells tens of kilometers wide. Upon reaching the cold surface, the nitrogen ice cools and sinks back down along the cell boundaries. This continuous, slow-motion, convective churning constantly resurfaces Sputnik Planitia, erasing ancient impact craters as fast as they can form. Surrounding the smooth nitrogen plains, New Horizons photographed majestic mountain ranges rising up to 11,000 feet into the sky.
named Hilary Montes and Norgay Montes after the first explorers to conquer Mount Everest. These towering peaks presented a mechanical puzzle.
Nitrogen and methane ice are far too soft at Pluto's surface temperatures to support mountains of such massive height. Under their own weight, nitrogen mountains would collapse and slump within short geological timescales. Spectroscopic measurements solved the mystery. The bedrock of Pluto is composed of solid water ice. At the extreme surface temperatures of Pluto, which hover near -390 degrees Fahrenheit, water ice behaves like rock, forming a rigid crust capable of supporting towering mountain ranges. Floating on top of this rock-hard water ice bedrock are vast glaciers of soft nitrogen and methane ice that flow through mountain valleys like alpine glaciers on Earth. Beyond mountains and nitrogen plains, New Horizons provided compelling evidence for a subsurface liquid ocean concealed deep beneath Pluto's icy shell. Scientists observed that Sputnik Planitia lies aligned almost perfectly opposite to the tidal axis connecting Pluto and its giant moon Charon. Such an alignment strongly suggests a mass anomaly, a region of concentrated extra mass that gravity has locked into position. To generate such extra mass beneath the surface basin, Pluto likely harbours a thick, slushy ocean of liquid water, mixed with ammonia acting as an antifreeze, buried beneath 100 kilometres of solid ice. The heavy liquid ocean upwelling into the basin area beneath Sputnik Planitia provides the gravitational weight needed to align the dwarf planet system. New Horizons also captured stunning views of Pluto's thin, hazy atmospheric envelope as the probe passed behind the world and looked back toward the Sun. Blue, layered hazes composed of organic Tholins stretch hundreds of miles above the surface, created when solar ultraviolet light breaks apart methane and nitrogen molecules in the high atmosphere. These complex organic compounds condense into tiny soot-like particles that slowly drift down to the surface, painting large equatorial regions of Pluto in deep, rich shades of reddish-brown. The mission did not stop at Pluto alone. It also provided breathtaking close-up images of Pluto's massive moon Charon. Rather than being a drab, cratered satellite, Charon displayed a fractured, dramatic landscape characterized by a massive canyon system 4 times deeper than the Grand Canyon and stretching over 1,000 miles across its equator. Its northern polar region features a dark reddish cap nicknamed Mordor Macula, formed when methane gas escaping from Pluto is gravitationally captured by Charon, freezes onto its frigid pole, and is transformed into dark organic Tholins by cosmic radiation. The encounter between New Horizons and Pluto stands as one of the greatest achievements in the history of space exploration. In a single day, humanity transformed a mysterious, distant dot of light into a dynamic, living world of nitrogen glaciers, water ice mountains, exotic atmospheric chemistry, and hidden subterranean oceans. The flyby proved beyond doubt that distant worlds at the edge of the solar system are not static, dead remnants, but complex planetary ecosystems capable of driving geological activity across cosmic time. Following its historic encounter with Pluto in July 2015, the New Horizons spacecraft was still in prime operational condition, carrying remaining propellant and sailing through the outer fringe of the Kuiper Belt at high speed. However, its grand voyage through the outer frontier was far from over. Planetary scientists at the National Aeronautics and Space Administration had designed the extended mission with an audacious goal: to execute a close flyby of a small, pristine classical Kuiper Belt object. While Pluto is a massive dwarf planet shaped by geological activity, heating and internal evolution, smaller classical objects are thought to have remained exceptionally well preserved since their formation. Finding and targeting one of these tiny, ancient worldlets was essential for understanding the raw, unadulterated building blocks of our planetary system. Locating a suitable target along New Horizons' trajectory presented an extraordinary observational challenge. Scientists had to find a small object, only a few miles wide, located billions of miles from Earth, situated directly within the narrow cone of space accessible by the remaining fuel on board the spacecraft. In 2014, using the high-resolution instruments of the Hubble Space Telescope, astronomers conducted an intensive search across the background field of distant stars. They successfully identified a faint target initially designated 2014 MU69, which was later temporarily nicknamed Ultima Thule, a classical term signifying a place beyond the known world. The target was eventually officially named Arrokoth, a Native American term from the Powhatan language meaning sky. Navigating New Horizons toward Arrokoth required unprecedented celestial mechanics and tracking precision. On January 1, 2019, at a distance of over 4 billion miles from Earth, New Horizons made its historic flyby, passing just 2,200 miles from the surface of Arrokoth. This event marked the most distant planetary flyby in human history, capturing close-up images and scientific measurements of an object located deeper in the outer darkness than any world visited before. When the high-resolution images taken by New Horizons arrived on Earth, they revealed an astonishing physical structure that stunned astronomers worldwide. Arrokoth was not a jagged, cratered asteroid or a single spherical ball of ice. Instead, it was revealed to be a pristine contact binary, a single celestial body composed of two distinct flattened lobes joined together by a narrow, bright neck. Measuring roughly 22 miles long, 14 miles wide, and 6 miles thick, Arrokoth resembled a giant reddish cosmic snowman tumbling slowly through space once every 15.9 hours. The two lobes of Arrokoth displayed remarkably different geometric shapes. The larger lobe, named Wenu, was found to be relatively flat, resembling a thick pancake, while the smaller lobe, named Weo, was more bulbous and rounded, resembling a squashed walnut. The entire object exhibited a uniform deep reddish colour on its surface, caused by the long-term irradiation of simple hydrocarbon ice mixtures by galactic cosmic rays and solar ultraviolet radiation, creating complex organic Tholin compounds. High-resolution spectroscopy confirmed that the surface is coated in water ice, methanol ice, and complex organic molecules, devoid of volatile gases like nitrogen or methane, which easily escape small bodies. The structural geometry of Arrokoth provided planetary scientists with an incredible scientific treasure, an undeniable physical blueprint showing how planets began to form during the infancy of our solar nebula over 4.5 billion years ago. For decades, two competing theoretical models sought to explain how tiny grains of dust and ice grew into large planetary bodies. The first traditional model was the hierarchical accretion theory, which proposed that planetesimals grew through high-velocity, violent collisions between rocky and icy fragments, smashing together repeatedly until gravity accumulated enough mass to build a world. The second, more modern framework was the pebble accretion and streaming instability theory. This model proposed that gas drag in the dense primordial solar nebula caused tiny pebbles and icy grains to clump together gently into localized rotating clouds. As these dust clouds grew denser, their mutual gravity caused them to gently collapse inward under their own weight, forming planetesimals through a soft, low-speed assembly process rather than destructive, high-speed impacts. Arrokoth provided definitive physical evidence favoring the streaming instability and gentle collapse model. The junction connecting the two lobes, the narrow, bright neck joining Wenu and Weo, showed zero structural damage, fracturing, or shock deformation. If the two lobes had collided at high speed, the force of the impact would have shattered both bodies into fragmented debris or severely cracked their interiors. Detailed impact physics calculations showed that the two independent lobes must have approached one another at an extraordinarily gentle pace, moving no faster than a slow human walking speed, roughly a few miles per hour, before merging together. Furthermore, both lobes of Arrokoth showed remarkable alignment in their rotational axes before joining, proving that they originally formed side by side within the exact same localized, swirling cloud of pebble-sized debris. Over short timescales, gravitational drag within the localized gas cloud drew the two growing bodies together into a mutual orbit, slowly draining their orbital energy until they gently touched, merging into a permanent binary structure without altering their gentle internal compositions. Surface inspection of Arrokoth revealed another crucial discovery. Its terrain is largely uniform and preserved. The surface features subtle mound-like subunits on its larger lobe, each measuring a few miles across. Scientists hypothesize that these mounds represent individual building blocks, the original primordial pebbles or planetesimals that gently coalesced to build the larger lobe during the initial cloud collapse. The surface also exhibits a surprisingly low density of impact craters, proving that the classical Kuiper Belt has experienced extremely few violent collisions over its 4.5 billion year history. Because Arrokoth is located in the cold, dynamically undisturbed realm of the cold classical Kuiper Belt, it has remained virtually untouched by external forces since the birth of our solar system. It was never heated by radioactive core decay, never subjected to internal volcanic melting, never disrupted by giant planet gravitational tides, and never baked by intense solar radiation. Arrokoth is, in the most literal scientific sense, a pristine cosmic fossil, a preserved sample of the original material that assembled the worlds of our solar system. The flyby of Arrokoth transformed our fundamental understanding of planetary formation. By photographing this ancient reddish snowman drifting quietly at the edge of the sun's light, New Horizons provided humanity with an intimate look at the very first step in the birth of planets. The mission demonstrated that the vast dark realm beyond Neptune is not merely home to dwarf worlds, but serves as a cosmic library storing the undisturbed, ancient building blocks from which our Earth and every world in the solar system were originally built. Despite the monumental discoveries made by deep sky observational surveys and robotic space missions like New Horizons, the Kuiper Belt remains one of the most enigmatic regions in our solar system. The deeper planetary scientists probe into this distant, frozen expanse, the more anomalies they uncover, puzzles that challenge existing models of solar system formation and orbital dynamics. Far from being a fully mapped and understood frontier, the outer edge of our cosmic backyard poses fundamental scientific mysteries that continue to intrigue astrophysicists. Among these unsolved riddles, two monumental phenomena stand out: the abrupt, unexplained drop-off in population known as the Kuiper Cliff, and the compelling gravitational evidence hinting at the existence of an undiscovered, massive world lurking in the outer darkness, commonly referred to as Planet 9. To understand the mystery of the Kuiper Cliff, one must examine the overall spatial distribution of icy bodies beyond Neptune. Moving outward from the Sun, the density of objects in the Kuiper Belt gradually increases, reaching its highest concentration within the classical region between 40 and 48 astronomical units. Based on observations of planet formation around other stars and computer simulations of our primordial solar nebula, scientists originally expected this disk of icy debris to taper off gradually, stretching continuously outward across hundreds of astronomical units before smoothly transitioning into the distant Oort cloud. However, observational data reveals a radically different and shocking reality. At approximately 50 astronomical units from the Sun, the population of classical Kuiper Belt objects drops off precipitously, plunging almost to zero. This sudden, dramatic boundary in the density of space rocks is known in planetary science as the Kuiper Cliff. Beyond 50 astronomical units, the dense ring of frozen worldlets seems to vanish overnight, leaving behind an unexpectedly barren zone that defies theoretical expectations. For decades, astronomers attempted to explain away the Kuiper Cliff as an observational illusion driven by technological limitations. They argued that because objects at 50 astronomical units reflect significantly less sunlight than those closer to Earth, existing optical telescopes were simply not sensitive enough to detect them. However, as wide-field digital sky surveys improved, utilizing massive optical instruments and infrared sensors capable of detecting extremely faint celestial bodies, the cliff persisted. Astronomers discovered scattered disk objects traveling along highly eccentric, elongated paths that take them far past 50 astronomical units, yet the population of traditional, circular orbit classical objects remains virtually non-existent past this 50 astronomical unit line. The persistence of the Kuiper Cliff has forced astrophysicists to formulate several competing hypotheses to explain its existence. One prominent theory suggests that an ancient, undiscovered planetary body, perhaps a rogue planet or an unmapped massive world, once orbited in this region, using its gravitational power to sweep up or eject almost all planetesimals beyond 50 astronomical units, effectively cutting a sharp edge into the outer disk. Another hypothesis posits that during the infancy of our solar system, a passing neighbouring star drifted unusually close to our nascent sun's outer protoplanetary disk. The intense gravitational field of this passing star could have stripped away the outer edges of the disk beyond 50 astronomical units, truncating the original Kuiper Belt and scattering its outer inhabitants into interstellar space. A third possibility involves subtle chemical and physical dynamics during the formation of the early solar system. It is possible that the original solar nebula simply ran out of dense, solid material at 50 astronomical units, preventing small dust grains from sticking together efficiently enough to form large, icy bodies beyond that threshold. Regardless of which mechanism proves correct, the Kuiper Cliff stands as a major unsolved mystery, marking a sharp, unexpected physical boundary at the outer edge of the classical Kuiper Belt. While the Kuiper Cliff represents a mystery of missing objects, an even more captivating puzzle involves the strange, highly organised behaviour of the extreme objects that do exist in the far outer reaches of our solar system. In 2014, planetary scientists Chad Trujillo and Scott Shepard published a landmark observational study analysing the orbits of extreme trans-Neptunian objects, icy bodies whose closest approach to the Sun places them far beyond the gravitational influence of Neptune, typically exceeding 50 astronomical units, with average orbital distances stretching across hundreds of astronomical units. Trujillo and Shepard noticed a baffling anomaly. These extreme objects, including Sedna and another distant world designated 2012 VP113, all shared a remarkably similar orbital alignment. Specifically, their arguments of perihelion, the geometric angle describing the point in an orbit where a body comes closest to the Sun, were clustered around nearly identical values. In a completely random, chaotic outer solar system, the orbital orientations of these distant bodies should be distributed evenly in all directions. Early analyses estimated a low probability for such an alignment to arise by chance, although later work has emphasized the possible influence of observational selection effects. Building upon these initial findings, astrophysicists Konstantin Batygin and Mike Brown at the California Institute of Technology conducted a comprehensive mathematical analysis and dynamic computer simulation in 2016. Their research revealed that the anomaly extended far beyond a single orbital parameter. Batygin and Brown demonstrated that the orbits of 6 extremely distant trans-Neptunian objects were not only aligned in physical direction, but were also tilted at almost the exact same angle relative to the flat plane of the major planets. Furthermore, these extreme orbits were physically clustered in physical space, pointing toward the exact same quadrant of the night sky. Within these models, the persistent alignment is difficult to reproduce using only the known giant planets or galactic tides, although alternative explanations and observational biases remain under study. Something in the distant darkness was actively manipulating their paths, acting as a massive gravitational conductor directing a cosmic orchestra. To explain this extraordinary phenomenon, Batygin and Brown proposed a widely discussed hypothesis. The apparent gravitational clustering of extreme trans-Neptunian objects could be caused by an unseen, massive ninth planet orbiting in the deep outer fringes of our solar system. This hypothetical world, designated Planet 9, is predicted to be a super-Earth or mini-Neptune, possessing a mass roughly 5 to 10 times greater than Earth and a diameter 2 to 4 times larger than our home planet. According to detailed orbital modelling, Planet 9 moves along an extraordinarily stretched out, highly inclined eccentric orbit that takes it between 400 and 800 astronomical units from the Sun. A single complete circuit around our central star would take Planet 9 anywhere from 10,000 to 20,000 Earth years. At its aphelion, this dark, massive world would be located nearly 20 times further away than Neptune, drifting in a frozen region where sunlight is thousands of times fainter than on Earth. If Planet 9 exists, its dynamic influence could explain several reported anomalies in the outer solar system simultaneously. Computer simulations show that a planet with these mass and orbital parameters could produce distant, small, icy bodies into the exact anti-aligned clustered trajectories that astronomers observe today. As Planet 9 travels along its massive path, its gravity continuously nudges the perihelia of smaller objects away from its own position, sweeping their orbits into a tight, clustered bundle on the opposite side of the Sun. Beyond explaining the alignment of extreme trans-Neptunian objects, the Planet 9 hypothesis solves another long-standing cosmic puzzle: the existence of highly inclined perpendicular orbits. Astronomers have discovered a small population of extreme icy bodies whose orbits are tilted nearly 90 degrees relative to the planetary plane, essentially orbiting the Sun vertically. Simulations show that gravitational interactions with a tilted, distant Planet 9 naturally torque smaller bodies out of the main orbital plane, twisting their trajectories into high inclination and perpendicular paths over hundreds of millions of years. Despite the suggestive mathematical evidence and success of computer models, Planet 9 has not yet been directly imaged by optical or infrared telescopes. The search for this elusive world represents one of the most intense observational hunts in modern astronomy. Detecting Planet 9 is extraordinarily difficult due to several factors. Because it is located hundreds of astronomical units away, it reflects almost no sunlight, making it thousands of times fainter than Pluto. Furthermore, because its predicted orbit is so vast, scientists cannot pinpoint its exact position along its multi-millennial path, requiring them to search through large swathes of the night sky using powerful, wide-field telescopes like the Subaru telescope in Hawaii and the Vera Rubin observatory in Chile. Where could such a massive world have come from? Astrophysicists suggest two main theories for the origin of Planet 9. The first theory suggests that Planet 9 formed alongside Jupiter, Saturn, Uranus and Neptune in the inner giant planet region during the early days of the solar system. During the chaotic epoch of planetary migration, a close gravitational flyby with Jupiter or Saturn may have flung Planet 9 outward onto an extreme, highly elongated path, where interactions with passing neighbouring stars in the Sun's birth cluster stabilised its perihelion, preventing it from being ejected completely into interstellar space. The second, more exotic theory proposes that Planet 9 was originally a rogue planet or an exoplanet captured from a neighbouring star during an ancient stellar encounter in the early solar nursery. The mysteries of the Kuiper Cliff and Planet 9 highlight the profound gaps that remain in our understanding of our own planetary neighbourhood. The outer solar system is not a static, fully mapped territory, but a dynamic and mysterious frontier holding fundamental clues to our origin. Whether the sharp edge of the Kuiper Belt was carved by stellar encounters, or whether the unseen gravitational hand of Planet 9 is confirmed by direct telescope imaging in the coming years, these unresolved questions prove that the dark outer reaches of space still hold magnificent secrets waiting to be unveiled. As humanity gazes into the vast darkness beyond Neptune, we stand on the threshold of a revolutionary era in astronomical exploration. The story of the Kuiper Belt, once a theoretical speculation and later an unexpected realm of icy worldlets, is now unfolding into one of the most dynamic frontiers of modern astrophysics. The tools and technologies currently being deployed, combined with future interstellar missions and long-term astrophysical models, promise to transform our understanding of this frozen kingdom. Far from being a distant, static fringe of our solar system, the Kuiper Belt represents a gateway to deciphering our cosmic past, our present observational limitations, and the ultimate long-term destiny of our planetary neighbourhood. At the forefront of this new era of discovery stands the James Webb Space Telescope. Positioned at the second Lagrange point, roughly 1 million miles from Earth, this flagship observatory is uniquely equipped to pierce the dark mysteries of the outer solar system. Unlike traditional optical telescopes, the James Webb Space Telescope operates primarily in the infrared spectrum, allowing it to detect the faint thermal glow emitted by cold, icy bodies billions of miles away. Because volatile compounds like water ice, methane, carbon monoxide, nitrogen and complex organic polymers possess distinct chemical absorption lines in infrared wavelengths, Webb can perform high-resolution spectroscopic analysis on distant dwarf planets and small classical objects with unprecedented sensitivity. Early observations by the James Webb Space Telescope have already begun to yield astounding insights into the chemical diversity of the outer frontier. By analysing the surface compositions of distant bodies like Eris, Makemake, Sedna and Gong, Webb has detected subtle chemical signatures that were previously completely invisible to ground-based observatories. Scientists can now map the regional distribution of frozen volatiles across the surfaces of dwarf planets, track atmospheric sublimation cycles, and search for active cryovolcanism, or subsurface ocean venting. Furthermore, Webb's extreme spatial resolution allows astronomers to search for tiny, previously undiscovered moons and faint ring systems surrounding classical Kuiper Belt objects, providing crucial data needed to calculate their precise masses, densities, and internal structures. Complementing space-based observatories like Webb are ground-based megaprojects, most notably the Vera C. Rubin Observatory in Chile. Utilizing a massive 8-meter mirror and a 3 billion pixel digital camera, the largest digital camera ever constructed for astronomy, the Rubin Observatory is conducting the legacy survey of space and time. Every few nights, this facility scans the entire visible night sky, mapping billions of celestial objects over a 10-year survey. Astronomers anticipate that the Rubin Observatory will discover tens of thousands of new Kuiper Belt objects, scattered disk bodies, and extreme trans-Neptunian objects, effectively increasing the catalogued population of the outer solar system by an order of magnitude. This massive dataset will allow scientists to map the precise three-dimensional structure of the belt, pin down the boundaries of the Kuiper Cliff, and potentially locate the elusive light of Planet 9. Looking further into the future, the next physical step in exploring this realm involves dedicated interstellar probes. While New Horizons provided breathtaking flyby snapshots of Pluto and Arrokoth, its path was restricted to a single narrow trajectory. Space agencies around the world are currently studying concepts for dedicated interstellar precursor missions. These proposed spacecraft would utilize advanced propulsion technologies, such as nuclear electric propulsion or solar sails, to travel at unprecedented speeds toward the edge of the heliosphere and beyond. An interstellar probe traveling at 4 to 5 times the speed of Voyager 1 could cross the Kuiper Belt in less than a decade, visiting multiple dwarf planets, deploying atmospheric entry probes, or even entering orbit around a distant world to perform long-term geological and oceanographic studies. Beyond human exploration timelines lies an even more profound cosmic perspective, the distant future of the Kuiper Belt as our central star evolves. Today, the Kuiper Belt is an ultra-cold deep freeze, preserving primordial ice at temperatures hovering near absolute zero. However, this frozen state is not permanent. In roughly 5 billion years, our Sun will exhaust the hydrogen fuel in its core, initiating a dramatic physical transformation. As the Sun expands into a red giant, its outer layers will swell to encompass the orbits of Mercury, Venus, and likely Earth, rendering the inner solar system a scorched, uninhabitable wasteland of molten rock. As the Sun expands and its total luminosity increases thousands of times over, the cosmic habitable zone, the region around a star where temperatures allow liquid water to exist on a planetary surface, will sweep outward across the solar system. The icy realms that are currently frozen solid beyond Neptune will experience a dramatic environmental awakening. Distances between 30 and 50 astronomical units, where Pluto, Eris, Haumea and Makemake reside, will receive levels of solar energy comparable to what Earth receives today. During this red giant era, which will last for hundreds of millions of years, the frozen volatile crusts of Kuiper Belt objects will melt and vaporize. Vast glaciers of nitrogen, methane and water ice will thaw, forming dense atmospheres and expansive global oceans of liquid water across worlds like Pluto and Eris. The complex organic molecules and prebiotic chemical compounds that have been preserved in the deep freeze for billions of years will dissolve into warm, liquid environments, creating ideal conditions for complex organic chemistry. For a brief, glorious epoch in the late life of our solar system, the Kuiper Belt will be transformed from a frozen graveyard into a thriving, habitable oasis, a final sanctuary for life at the edge of space before our star ultimately collapses into a cold white dwarf. The journey to understand the Kuiper Belt is ultimately a journey to understand ourselves. From its theoretical origins, envisioned by Kenneth Edgeworth and Gerard Kuiper, to the groundbreaking discovery of 1992 QB1 by David Jewitt and Jane Liu, this distant ring of ice has repeatedly shattered our narrow assumptions about the universe. It has taught us that our planetary system was forged in chaotic gravitational violence, that giant planets migrated across vast distances, and that the seeds of Earth's oceans and biological life were likely delivered by icy wanderers hurled from the outer darkness. The Kuiper Belt reminds us that scientific discovery is an ongoing, evolving saga. Every answer provided by robotic explorers and powerful space telescopes uncovers a dozen new questions waiting to be answered. As we continue to scan the horizon for Planet 9, map the pristine architecture of ancient contact binaries like Arrokoth, and peer deeper into the dark expanse with instruments like the James Webb Space Telescope, we are reminded that humanity's quest for knowledge knows no final boundaries. The frozen frontier beyond Neptune is not the end of our solar system, but an invitation to explore the infinite mysteries that lie beyond.